On question 27, we are going to look at how we would sketch the graph of the given function, being sure we identify local extrema and points of inflection. So we will first start with our first derivative. So here is my first derivative. I set it equal to 0, and then notice that I set both factors equal to 0, and I have my critical values. So x is negative 2/3 and x is equal to 2. So building my number line here with those critical values, if we plug in something less than negative 2/3, I just thought x equal -1 would be easy. Remember, you're plugging those back into your first derivative because you're interested in what is the derivative doing on that interval. And when I plugged it in, I got a +3, so positive, which means the graph is increasing on that interval. In between these two critical points, I used x equals 0, just easy to plug in. And in that case, I got a -4, so that tells me the graph is decreasing on that interval. And then finally, when I need to plug in something bigger than 2, I just decided to use x equal 3. I got a +11, so that indicates that the graph is increasing on that interval. So when a graph changes from increasing to decreasing, we know that we get a maximum here. And so that is the x-coordinate. The negative 2/3 is my x-coordinate of that maximum. In order to get the y-coordinate, you have to plug this x back into the original function. And I actually came all the way down here to show you that by hand. I do not care if you punch it out on a calculator, but if you punch it out on a calculator, at least show me this part where you plugged it in. So I went ahead and did it all by hand, just because, but definitely show me how you would plug it in or what you would be plugging into the calculator to get that y value. Okay, so then when a graph changes from decreasing to increasing, you get what we call a minimum. So in that case, my x value of my minimum is the 2. And then in order to find my y value, again, I came all the way over here and I plugged 2 into the original function right there. And once again, you could plug it into a calculator at that point. That one wasn't as difficult because it's not a fraction, but you are looking for the y value, so you've got to know to go back to your original function when you're looking for actual points on the graph. Okay, so then we're looking for points of inflection. We have to associate points of inflection with a second derivative. So I came back to the original first derivative, took my second derivative here, set it equal to 0, and a possible point of inflection I found was 2/3. So I made my number line here. Choosing something smaller than 2/3, I plugged in x equals 0. You're plugging into your second derivative because you're interested in what the concavity is doing on that interval. So I got a negative answer, which tells me that the graph is concave down on that interval. And then I chose to plug in x equal 1 for a value bigger than 2/3. And when I did that, I got a +2, which tells me the graph is concave up. So that x equal 2/3 is definitely a point of inflection. They want the ordered pair, so I came all the way over here and plugged the value 2/3 into my original function. Again, you can get on a calculator at this point if you want, but show me how you plugged it in first. And we get a y value of -61/27 for that point of inflection. And then finally, I had you choose the correct graph. It got cut off on my copy that I printed out, so I actually drew the picture for you here. It should have been D. So the main things that you're looking for when you're looking at that graph is that if you say that there is a maximum at -2/3, you should clearly see that maximum on the graph. Minimum at 2, -7, you should see that. And then, of course, where it changes from being concave down to concave up, you should have your point of inflection. So just make sure when you're looking at those that you're seeing those points on the graph.